Okay, bit of theory. Low pass filter, high pass filter. What do we want a filter for? Someone tell me why we want a filter.
Remove noise.
To remove noise. So, alright. Never give me an answer and I won't give you a question back. What's noise?
Annoying.
Annoying, something that's there that you don't want. Okay, so it's an unwanted part of the signal. So filters remove unwanted signals. So that means that I've got something that's frequency selective. So on your phone, for example, you might think that when you're talking to someone that's actually pretty high quality. It's rubbish. I mean, it goes from 0 to about 3.4 kilohertz, thousands of hertz, not millions of hertz. And you might think that you can recognise your friend on the other end, but actually that's only because you've spoken to them lots of times before. The quality's appalling. So I've really got not many different types of filters, but I've got low pass, which means it's going to let low frequency through. Remember from last time? Yeah. I've got high pass, which lets high frequency through. Okay, so when would I use a low pass, do you think? When would I want to use a low pass filter?
Like high frequencies?
Yeah, absolutely, but I mean a practical example, well I just practically gave it away to you. There's one sat on the table there. So on a telephone, you don't want high frequency squeaks and bumps and hisses and all that kind of stuff. But, you know, my voice particularly, but most people's voices are recognisable just with the frequency below about 3.4 kilohertz. So you're going to filter all of the high frequency out. You don't want it, it serves no purpose. So that's the kind of thing that you would use a low pass filter for. What about a high pass filter? So phone speech. What about a high pass filter? Why would you want to block the low frequency and let the high frequency through? Think of an example? Okay, well, here's an example. Have you never turned on your hi-fi in your house and you're playing your music but there's an annoying in the background? Well, that's mains hum, that's 50 hertz. We can get rid of that because if we have a high-pass filter, and that might be used for stuff like music, etc., we would design a filter to get rid of that 50 hertz completely, block it completely, but the higher frequencies just let them through. So that's a pretty useful thing to be able to do. Another type of filter that we can use is a band pass filter. So let's just draw a graph of what these look like. So a low pass filter looks like this. A high pass filter looks like this. So this is frequency and this is amplitude here. We can have a band pass filter. What's the band pass filter look like? Well, it looks like this. So it blocks this, it lets this through, and it blocks this. That's A, that's F again. So that's band pass. We can have a band block. We can have a band block filter. So we can have a filter that looks like this. In other words, it lets everything through apart from the frequency that we're trying to block. There are others. So you can have what's called a cone filter, which is lots and lots and lots of slots, but really all they are is lots and lots of filters all added together. But they're your main ones. Band pass, that you find that in TVs and things like that for selecting signals. And the same with the band block, you would find that inside a high quality RTF radio telephone. Okay, so that would be a radio transmitter like a CB radio or a amateur radio enthusiast's rig. Okay, so there are your different kinds of filters. Well, we touched on, does anyone want to photograph that before I remove it? It will be on the YouTube video if you... I did see lots of people are looking at that, by the way, so I'll upload it as soon as I get back to my office and you can see the stuff that we did today if you didn't understand something. Okay, so remember last week we started inserting capacitors in instead of resistors, but a really quick recap, and it will be lightning fast. If that's R1, that's R2, that's my input, that's my output. My output is defined by, I'll pull this B in, that's B out. So V out is equal to V in R2 upon R1 plus R2. That's the building block of all our filters. Yet remember, they're resistors, so they don't do anything, they just let all the frequencies through. But what they do is they just trim the amplitude according to the ratio of this one and this one, according to that equation, basically. Now what we started messing about with last week was, well, what happens if I make one of those a reactive component? In other words, we saw that XL equals 2 pi FL, or omega L, and XC equals 1 upon 2 pi FC, and we saw that those components behave differently at different frequencies. That's the important thing. So we're going to exploit that to make ourselves a filter. So let's do a low pass first. So if I do draw this, so I'm just going to use an abbreviation LP for low pass. If I draw this, that's V in, and that's V out. So what, how does that help me? Where's my filter? Where's my design numbers? How do I work out whether I cut off at the right frequency and all the rest of it? How do I know these things? Well, I can work it out directly because I can know the reactance of the individual device, can't I? Yeah. Another thing I can actually do is I can... You're thinking out loud, okay. That's good actually, I think out loud, but if people think you're talking to yourself at the same time. So we know from this that if we put a high frequency in here, this thing here will go short circuit, because that's what capacitors do, they conduct high frequency. So the capacitor just goes short circuit, it takes all of the output and conducts it to ground. Yeah? So it's blocking high frequency, it's shorting high frequency out. At low frequency, this is just an open gap, and it lets it all through. So it's letting the low through and blocking the high. Now it would be quite nice if we had a way in which we could express that so that we knew what the design equation was for that. Can anyone help me with that? The cut-off point. So if I want this, if I want the cut-off frequency. Now the cut-off frequency is quite difficult to define, but needless to say, so we're low passing, and then all of a sudden it starts to head down towards zero. We acknowledge that because this goes into conduction. But what we'd like to know is, well, we could take this point here, but of course that's a gentle slope all the way down, so it doesn't mean much. We could take this point here, but of course it's already gone down to zero at that point. So what we tend to do is we take 1 upon root 2 here, or 7071, and we say when the amplitude has dropped by 1 minus 0.7071, we say that that's the cut-off point. So we say this point here is cut off, or the frequency for cut-off. Yeah, now that's a useful thing to be able to do, because now someone says to me, design a filter with a cut-off frequency of 10 kilohertz. Now I can do it, because I can plug the numbers in. So I put 10,000 in here, I've got 1 upon 2 pi, that doesn't change. C, I don't know. R, I don't know. But I can assume one or the other, so if then I say, well, I'm going to make R 10K, because I like 10K, then the only variable left is the C, and if I rearrange the equation, I've then designed a filter with this kind of cut-off, a low-pass filter, which is 3 dBs down at the point of cut-off according to the numbers that I plugged in here. I've done it. I've designed a filter, not just trial and error. You know, it works okay, so I increase the size of the capacitor. I don't know. It's really, really useful, right? All right, let's do one. So I want and 20 kilohertz is typical for high quality audio, because it's difficult, especially if you're old like me, to hear really high frequency. Let's say 20 kilohertz, we can't hear anything above 20 kilohertz. So why not build a filter that knocks everything out beyond 20 kilohertz, and then we don't have to amplify it at all, and it makes our amplifier really simple because we can use low quality components that only are going to magnify frequencies up to 20 kilohertz. So I want you to design me a filter with a frequency cut-off of 20, well, let's just use the numbers so nobody gets confused.